this, that, and the other. I know we were talking to HR, but I didn't know what it was about, and he was just like, he showed her the patch, and I was like,
Sit right here.
"God,
So, if I ever find.
should I leave? I think I should be here."
Make sure the right amount of triangle that you want.
Well,
So other than. I didn't really pay attention to them.
About the attendance, and I see you guys put X's and O's like Tic Tac. I'm not sure, but just put an X in.
It's like Ishan. Why did you just tell?
No, it's like, why did you put X's? We were like,
Oh, yeah.
yeah.
You want the other way.
Is this technically lecture 5 or is this lecture 6?
This is lecture 5.
Okay, so you
Yeah.
just wanna like, okay, so,
It's okay, just put for 5. Yeah.
okay. My name.
This is like reverse paper.
Yeah.
It's the same. We didn't finish it. We didn't get the first one. We did lecture 3. So yes,
They did tomorrow. Never been 360 Richard. I was gonna do it.
31. Oh, I moved really hard.
Yeah.
I haven't really done yet. I'm finishing it. I really understand the first part. And yeah, it took me a second to like, I had to like keep going with it and come back to one because I didn't know.
Yeah.
I was about to ask you how loud was, Brian.
Was it last month?
Oh, yeah, number 1. We have one phones. But
Yeah.
yeah.
So we didn't get to
Yeah.
Thursday. That's what I know. I'm sorry.
I'm still dealing with my hand hurting. Yeah.
So today's class is actually going to be a little different. Like, it's going to be a little bit of math. No, it's going to be fun math. Okay. No. Just follow along. Okay. So I haven't uploaded the slides here, but I will upload it today. Okay. So it's just an add-on to what's going to come next.
Short. Yeah, one long.
So any questions before we start? Any questions on the previous two classes about the assignment? I will go over the question one in the assignment in basically this set of slides because this is the one where I'll talk mainly about Rent's rule and stuff like that. So once I discuss that, the first question in the homework will be fine. Okay. So yeah, so I think we can get started. So in this set of slides, I wanted to do something a little bit different, something that I kind of haven't done before. So I wanted to explain basically the concept of chip scaling as well as how chips communicate through the package, but using a kind of a game. Okay, and I'll talk about the rules of how this game is played, and then played as in like how the rules of this game work, and then how from this we can actually understand something which is called as Rent's rule, which talks about the relationship between the number of functional blocks in a chip. Functional block could be anything, it could be gates, it could be logic blocks, and so on. So it tells you the relationship between the number of blocks within the chip as well as the number of terminals coming out of the chip. Okay. So ultimately, what we want to do is we want to understand that imagine you have a chip. And so I'm going to define something called as a logical block. Okay. And then logical block can be anything. It can be a single gate. How many of you are familiar with the concept of gates and all that? I'm sure most of you are, right? What?
You asked how many, and I raised.
You are, okay. Okay. Yeah, so no matter what digital circuit is, it's basically a bunch of, for example, NAND gate, NOR gates, and so on connected together. And each gate itself can be realized using transistors, right? And so each block basically represents a bunch of gates and these kind of digital circuits which are connected to each other. And so what we're going to do is, so we have a chip. And what we're going to assume is that inside the chip, all the logical blocks are identical. So we have the total number of logical blocks within the chip is say V, and then the number of terminals which are actually coming out of the chip. The terminals being the actual things that you're going to connect to the outside world. Okay. So we're going to find a relationship between the number of terminals coming out of the chip as well as the number of actual logical blocks within the chip. Okay. And what you'll find is that this relationship between the number of terminals and number of blocks is actually a power law. And the reason why it's a power law has something very deep to do with a concept in math called fractals. I don't know how many of you have heard of this thing called fractals, but we'll talk about fractals. A very good example of fractals is snowflakes. Snowflakes are fractals, okay? So fractal is basically a kind of geometry where it has the property of self-similarity, okay? Look, so I can easily draw a fractal. So this is an example of a fractal. So if I continue this to infinity, right? So imagine this is spreading out throughout, and I'm just continuing this all the way, it gets smaller and smaller and smaller and smaller. This is an example of a fractal, okay? And the defining feature of a fractal is that at this scale, it looks the same as when I magnify it, okay? So imagine I took a magnifying lens and I looked over here. This will look the same as if I looked at this from zooming out. Okay, so it is something called scale invariant. So it doesn't matter whether I'm looking at from far away or whether I zoom in and look at it, it looks exactly the same. So can you tell me some examples of where this kind of structure is found?
No.
Yeah, actually it's found everywhere yeah. Sorry? Yes, you're right. And we'll talk about coastlines, okay?
Forest fires.
No.
No.
But every kind of natural structure that you observe is generally tends to be a fractal. For example, your circulatory system is a fractal because you have those large arteries and veins, but then you magnify and look, there are smaller arteries and veins, and then you go smaller and smaller, you go to capillaries and so on. But no matter which scale you look at, it looks very similar, right? Similarly in a tree branch, right? So whether you look at the whole tree or you look at a magnified view of a single branch, it looks similar, right? That is a fractal. And actually, fractal geometry explains in a way how this T and V are related, and they're related by a power law. Okay, and we'll see how that works. So, this is one concept we'll use. Another concept we'll use is the relationship between the area and the perimeter. Okay. So for example, imagine I had a square, right? So the square, the area is a square, if a is the side, and the perimeter is 4a. So what is the relationship between area and perimeter, right? So if I take a is square root of, so square root of a equals p over 4. And so the perimeter is 4 times square root of a, right? So essentially the perimeter is proportional to a power 0.5. Correct? And how does this vary? If you had, so this is in 2 dimensions, right? So if I had a square and I had a side A perimeter, this is a relationship between the area and the perimeter, right? What if instead I had, for example, a cube? So if I had a cube and you work this out, the volume is a cube and the surface area is 6a squared. And if you do the same kind of thing over here, you'll find that the volume is related to the surface area, but by 2/3. Okay. So you'll find that, and it's interesting, but you can mathematically do this for any dimension. Okay. Say up to n dimensions, right? What do you think it would be for 1 dimension? So if it was just a line with 2 dots, what do you think it would be? So what is the analogous analogy between a square and just a line, right? So in a square, you're comparing area and perimeter. In a line, you're comparing the length and the boundary, which is the 2 dots, right? So in this case, if this is the length A, how is A related to whatever the boundary is? The answer is there's no relation, because no matter how big I make the A, it always has just 2 boundaries, right? So the relationship between the boundary and the length is to the power of 0. Okay, so for 1 dimension, it's to the power of 0. For 2 dimensions, it's the power of 0.5. 3 dimensions, it's the power of 0.667. And then it keeps going, but it never quite goes to 1. Okay, and as you go to higher and higher dimensions, it gets closer and closer to 1. Okay. This is an interesting mathematical fact which will be useful in explaining how this works. Okay. I know this looks kind of scary, but believe me, it's kind of quite easy to understand. But any questions so far? Okay. So what we're going to do is we're going to consider that the entire chip is made up of logical blocks, as I mentioned. And so each logical block inside it has a bunch of gates, which are connected in some fashion, right? So it can be anything, right? And so the chip itself is going to be made by a bunch of logical blocks, which are connected in some arbitrary fashion, right? So it can be a regular connection. For simplicity, I assumed a regular connection, but it can be even some random connection, right? And so what we're going to do is we're going to establish the relationship between the number of blocks inside this chip, as well as the number of terminals that's actually coming out of this chip, right? Which is the actual thing that's going to connect to a package, right? So let's do this iteratively, right? So this, whenever you have a problem like this, the best way to do it is reductionist. So you start from the simple case and then you keep making it more and more complicated, right? So if I just had a single block, just a single logical block, number of block is 1, number of terminals is 4, right? Now imagine I had 4. And the way I'm going to do this is right now for this kind of an architecture, what architecture means is it means how I'm connecting the blocks together. Okay, so I'm assuming an architecture where I'm connecting the blocks next to each other in this kind of square mesh. Okay, so if I had 4 blocks, then what happens? I have B equals 4 blocks, and I have 8 terminals coming out, right? And then if I keep doing this for, let's say this is 16, B16, T16, and then you see this keeps going up, right? But you see, as B is increasing by factors of 4, so it's going 4, 16, 64, 256, T is not actually increasing that fast, correct? And so if you keep doing this, so, B is 1024 here, T is 128. So now the question is, as B tends to infinity, what is the relation between B and T? So I'm just going to give 2 minutes for you guys to think about how you would think about the relationship between the number of blocks as well as the number of terminals coming out, as number of blocks, for example, tends to infinity. And you're going to make use of this somehow. Okay, you're going to make use of this fact somehow. Just think about it. Anyone has the answer? Think about what you're counting here, right? Just think about what you're counting here. When you count the number of terminals here and the number of blocks.
The perimeter,
Exactly. Yeah.
is it feet to the power of however many?
Yeah. So as the blocks are getting smaller, right? Actually, what you're doing here, if you look at how I'm trying to explain electronics with this, right? When you're increasing the number of blocks, what you're actually doing is you're scaling down the logic blocks, which is what Moore's law is, right? So with every technology node, you're scaling down the blocks. So what I'm doing is when the blocks get very small, when I count the blocks, what am I actually counting? I'm counting the area within the square, correct? And when I'm counting the number of terminals at the very edge of this that's coming out, what I'm counting is actually the perimeter of the square. That makes sense, right? So when I talk about the relationship between the number of blocks within this, as well as the number of terminals which are coming out from the periphery, I'm really talking about the relationship between the area and the perimeter of the square, correct? So this would be the relation. So the number of terminals coming out would just be related to the number of blocks within this to the power of 0.5, similar to that square, times some constant k, okay? So k, and what k is just the number of terminals coming out of a single block. You can verify that if I put b equals 1 and I had one block, then k equals t, and therefore if I have just one block, I should have 4 terminals, right? So k has to be 4. So k is a constant, which is the number of terminals coming out of a single block. And the relationship between P and B would be 0.5, right? So it's a power law with a factor of 0.5, right? So you guys clear? Yeah.
How, how the perimeter relate? Or,
Yeah, so imagine I had a square, right? So what I'm essentially doing by this practice is I'm dividing it, say there's a grid, right? There's a grid like this. So when the blocks get smaller and smaller, what I'm actually doing by the number of blocks is I'm just adding these numbers, right? I'm just adding these things. And the number of terminals is I'm just adding these lengths, essentially. I'm basically counting the number of blocks within this and the number of blocks at the very edge, right? So have you taken calculus? Do you remember calculus? Okay, that's good. So if this is x and y, what I'm essentially doing is I have a block that's dx dy. And so what I'm doing is I'm doing dx dy integrated from here to here and here to here, which is just the area. And then I'm also doing integral dx across this boundary plus integral dy over here plus dx over here, dy over here, right? Which is just a perimeter. So the number of blocks inside this and the boundary of this are related by the relation between area and perimeter, right? As the blocks get smaller and smaller. And actually, if you don't like calculus, you can also do this in a different way, is you can actually make a computer count this and see how it goes as the blocks get smaller and smaller. And you'll see that it gets closer and closer to the power of 0.5. Because the relationship is the area perimeter relationship, right? So you can see how the relationship between the number of terminals on the block, number of terminals on the chip and the number of blocks within the chip tends to be a power law in this simple case, right? So now what I'm going to convince you is it has to be a power law, no matter what kind of connection comes out of it, okay? So whether it's a regular case like this, which is a regular architecture, or you have a case where you have some random distribution of wires, this relationship always holds. It'll always be some power law, but the only thing that will change is this exponent. So this exponent can be anything between 0 and 1, okay? And we'll see the meaning of what that actually means. When it's 0, when it's 0.5, when it's 1, what is the exponent actually telling you, right? So just looking at this kind of, just try to kindle your intuition, right? What is the exponent actually telling you, essentially, right? If the exponent was, actually, if I go to the next slide, that'll become more clearer. Okay, so what if I had a situation, so in the previous case, I had every block connected to the adjacent block, correct? Now imagine a situation where I have the same thing, I have a whole bunch of small blocks. I haven't drawn all of them, that's why it looks bigger. But now imagine that every block, all the terminals from it are taken to the perimeter, taken to the edge, right? So now the chip, every block within the chip is now contributing to the terminals at the outside of the chip, right? In this case, what do you think would be the relationship between T and B?
Then it'd be 1 to 1.
Yes, because since every block now contributes a terminal, when you look at the number of blocks, you're essentially counting the area. But when you look at the number of terminals, it's just going to be 4 times the area, right? Because each block is contributing 4. And because every block is now contributing, you essentially it's equivalent to you counting just the area, right? So now the relationship between B and T would just be 1. So you'll have T equals KB, right? So this will give you a clue. What does the exponent actually telling you? Think about it. What is the exponent telling you here?
That by increasing the amount of blocks, we're decreasing the amount of interconnects.
No, it's independent of the blocks. It has to do with how they're connected. So actually, the exponent is telling you how they're connected. But what is it actually telling you? Like compare this case where the exponent is now the maximum it can be, which is 1, versus a previous case where it's 0.5. Yeah.
It's just like a metric for how interconnected like
Exactly.
block is.
Yeah. Yeah. So the exponent is really telling you within a chip, how connected are the different blocks together, right? If more of them are communicating with each other and more connected, and they don't have to communicate that much with the outside world, then this exponent is often called as the rent exponent. Then the rent exponent will be smaller, right? So smaller rent exponent means within the chip, all the blocks tend to be connected and they don't have to communicate that much with the outside world. That means the whole system is almost self-contained. But if you have a situation like here, where every block is almost not even communicating with each other, but all the information has to come from the outside, that means there is no interaction within the chip. Everything has to come from outside. So that's the case where you have the maximum number of terminals, right? So in that case, the rent exponent would be the highest, which is 1. So the rent exponent is really telling you how well interconnected the system is, right? And yeah.
The goal is to generally reduce the rent.
Yes.
Have more interconnect.
Correct.
Okay.
Correct. So the goal is to reduce, the goal is to reduce rent exponent, because the more you reduce rent exponent, you design your chip, and I talk about later about how you do that, but you want to design the chip in such a way that the terminals coming out is less, which means you want to put most of the functionality within the chip itself and most of the dependence within the chip itself. Like that's the reason why, if you look at GPUs today, the compute and memory are placed on the same chip, right? That's why the GPU chip is so large. More functionality is put within the chip so that you don't have to go too much off chip, because going off chip is expensive, as you will see. This is clear, right? So now just think about this. In this case that I showed, where you have, all of these connected, and then on the periphery terminals coming out, it's 0.5. Every block giving terminals outside is 1. What if you had a situation like this? Okay. What if you had a situation like this, where I have one set of blocks connected, another set of blocks connected, but I place them one on top of each other, slightly shifted, right? So they look something like this. What do you think the relation between B and T here? So in this case, all I did was I took one set of logic blocks connected the way I described first, and I took another identical one, but then I placed them slightly offset. So I shifted this over here. So this is now more dense. So there's more dense blocks. And then now at the periphery, I have essentially twice the number of terminals coming up, right? So what do you think the relation between B and D is? Yeah.
0.25.
It's still 0.5. Because you're still counting the area and you're still counting the perimeter. So it's still 0.5. Okay. Yeah.
When you place them together, the interconnects doesn't change, right? It's still connecting to their own blocks. It's not interconnected.
So yeah, so actually, you know what? Since it's like, I think if I explain in detail how each and everything here works, it's gonna take a long time, but you can show that it's very difficult to get any number than 0.51. Okay. Just by thinking about it, like if you want to consider a case where you are looking at how to connect the wires in patterns, right? And you try all sort of things, you can sit down and try this experiment, just try different ways of connecting the blocks. You'll find that you'll only be able to get 0.51. You can't get anything other than that. Except what I'll talk about now is how do you get something other than 0.51? Okay. And that's the general case.
So you added more logic blocks, but the amount of interconnects.
Yeah, so I proportionally double the area, but I also proportionally double the terminals, right? So if I have, so for example, here in the original case, T was proportional to A power 0.5, right? Sorry, not A, B power 0.5. So now if I double the area, I've doubled the terminals, I've just multiplied it by a factor. I haven't changed the 0.5. Okay, I just multiplied everything by a constant.
I got a question, but if it's going down, would it not be 1 minus or something like that?
1 minus as
Yeah,
in?
because it looks like it's going down. Like if it were like an X and Y.
Mhm.
Because if you were to put them like on top of each other, you wouldn't be able to like
No, this
area would be.
this block, so in this case, it's 4 blocks here, right?
Yeah.
In this case, it's 4 blocks here, 1 block in the middle.
Okay.
Yeah, and the drawing, I mean, I just took this, copy pasted and put it together. That's why it looks like that. But I'm putting one more block here, and then this, and it has its own terminals here that's also coming out. That's why.
Okay, so that, okay, yeah.
So one side of that, the scaling on the board, that has to do with the Moore's law, right?
Yeah. I mean, right now it's just a concept, but this has to do with Moore's law. How Moore's law comes into play is this relation between B and P tends to, so as I'm increasing number of blocks I've shown, right? What I'm actually doing is I'm doing Moore's law scaling. Because within a given area, Moore's law says that within a given area, the number of logic blocks and the number of gates is doubling every 1.5 years. Okay. So it's an exponential relationship, right? So with every year, you're packing more and more transistors, which is equivalent to having more blocks within that area, right? But the important thing to understand is whether you're scaling down, it doesn't matter. The relation between B and T, as the blocks are getting smaller and smaller, is tending towards some power law, right? That power law for this kind of an architecture being 0.5, in the case where every block contributes being 1. Right, and usually it is some power law where where the rent exponent is somewhere between 0 and 1. Okay, so I'll explain now a case. I'll show you that exists. Okay. How many of you are mathematicians here? So you know in mathematics there's something called existence condition. No. So to prove, so the thing is here I've shown that 1 is possible, 0.5 is possible, and 0 is possible, right? But to show that every case is possible is a very hard problem to solve. But you can show an exception case. If I show it is possible to get something that's not 0.1, then presumably there are other possibilities. Right? That kind of argument is used in math very often, and that's the argument I'm going to use. Because actually proving this exists, I don't know how to do it because I'm not a mathematician, right? Okay, consider now this case, right? Where I have all these blocks connected, but at the very end, before the edge of the chip, I'm just shorting all these at one side, taking it out. So what would be the B-T relationship here? 1.4. It'll be 0. Because in this case, no matter what I scale, I'm always going to get 4 out because there are only 4 sides, right? So the number of terminals loses this relationship with B. Because irrespective of what B is, at the very end, I'm shorting this. So imagine I have more blocks here, right? It doesn't matter because I'm shorting everything in one edge, right? So I'm always going to get 4 terminals out, irrespective of what B is. Does that make sense?
So you're like putting like a metal layer over it.
Yeah, I mean, you can do this anyway. Yeah. So in this case, so if I take B and P, right? In this case, P is going to be always 4, irrespective of what the chip is, right? Because I'm always shorting all 4 sides. So if I put B over here, it's B power 0, right? Because B doesn't contribute. So the rent exponent here is 0. Does that make sense? So this is okay. So now I'm going to explain how I'm going to do an existence proof essentially and show you there's a possibility to have anything other than 0, 0.5, and 1. And I'm going to use the boundary of the US to prove that. Okay. Let's see how that works. So does anyone know? This is, I thought this was an interesting fact, but do you guys know where fractals? So fractals was discovered by a guy called Mandelbrot. I didn't say that right, but he was an IBM researcher, okay? And do you know what's the first real world application of fractals? Of fractals.
Like that type of structure.
Yeah. Like he developed the theory of understanding fractals. And then computer scientists took that fractals and did something with it. There was a place where it was first used in industry.
For pirates.
No. It's the the sixth Star Wars movie.
Six.
Yeah, so the sixth, which one is that? That's the
No, that's the fifth.
okay, it's the one. Yeah. Do you know that scene where I think the guy's Anakin and the other guy they fight in like No, not Luke. Okay, then I don't know which one is. Okay, I'm talking about the third prequel. Yeah. Anyway, but do you know that volcano scene, right? With all the mountains and all that? All that computer graphics was generated using fractals. Okay, that's why it looks so realistic. That was the first use of fractal geometry in industry. Okay. Okay, so where fractals first came, okay, where people understood fractals is people tried to study the relationship between, just like how you study the relationship between area within a square and the perimeter of square, people study the relationship between what is the area within, for example, a coastline. Everyone's smiling. Area within a coastline and the length of the coastline. Okay. So what it turns out is that for a given finite area within the coastline, the length of the coastline that you actually measure depends on the length of the scale you use. Okay. Because if you use a scale that's 1 meter long, say you can count and you can measure what is the length of the US boundary. But imagine you had a scale the size of a grain of sand, right? Then you start counting the grains of sand as well. And then it just keeps exploding, right? So it turns out in this case that if you calculate the length of the boundary versus the area, you won't get a simple 0.5 relationship, okay? So what you can do in this kind of a geometry is imagine you have this kind of complex geometry. The way people find out the relationship between area and perimeter is they use a computer, they divide it into a bunch of blocks as they get very small blocks. They count the number of blocks within this area as well as the number of blocks that are being cut by this line, right? And using that counting, you can then calculate what is the relation between perimeter and area. Okay. And what it turns out is that these kind of shapes, or any real world shapes, like for example, coastlines of countries, you find that this relationship is no longer an exact fraction. Like it's not a 0.5, and it ends up being some, for example, for the US, the relationship between the length of the US boundary to the area is 0.769. Okay. That somewhat makes sense? No?
Won't it depend like for different countries?
Yeah. This number, all you're doing here is very simple, right? You're taking a shape and you're dividing it into a bunch of grids. And you're counting the number of grids within this and the number of grids being cut by the boundary, right? And from that, you can measure you're essentially using a computer to find out what is the area within the shape and the length of the boundary of the shape, right?
That ratio right there, it depends on how small the grid is, right?
Yeah. But it actually settles. Like as you make the grid smaller and smaller, initially you'll get some number, but as you keep doing it, you find that the number goes and tends towards as n tends to infinity, or the size tends to 0, it will tend to this number. Okay. And that you call as it's called the fractional dimension of the shape. Okay. You don't have to understand the exact math of how this works, but whether you understand the math or not, you can appreciate the fact that for a simple shape like this, the relationship between perimeter and area has a 0.5, power law dependence. But for a complex shape, it need not be 0.5. It can be something that's fractional, like 0.7.
Some of those points in that grid, they like intersect to like one of those, like at the perimeter of the United States, where it could have more than one.
Yeah, so if you're doing this, if you had a boundary like this, right? How are you counting this, right? So imagine a small square here, a small square here, a small square here. So where this is cutting the square, I count that as one square being cut, right? And then I can do this using a computer as the squares get smaller and smaller and smaller, right? So if I plot what is the relationship between perimeter to area versus the number of squares that I have, you'll see that it starts some number and then it goes and then finally it starts settling somewhere as n becomes larger and larger. And this value it settles at is this 0.769.
Okay.
And that value is unique for like.
It's unique for every shape. It's called basically the fractional dimension of that shape, right? And this is the precise method, and this is called box counting, okay, this process. This is the precise method you use to characterize what the fractional dimension actually is telling you is, it's telling you that the shape is very rough. It's a measure of the roughness of the shape, okay? So, if the shape, for example, if you compare what is the fractional dimension of the US versus the fractional dimension of, for example, the United Kingdom, the United Kingdom's fractional dimension is way higher because it's an island and it's much more rougher at the edges. So it tends to have a higher fractional dimension. Okay, so it's actually a measure of the roughness of the boundary. Okay. So this is going to be a very hard pill to swallow, but no, not this. Next slide. But these are some examples of fractals in nature, okay? Most of the shapes that you observe in nature, for example, things like branches, leaves of ferns, and so on, all of them have the same kind of fractional dimension that you can actually calculate, okay? And truly, if you look at nature, right, most of the geometry is not regular polygon geometries. It is this fractional geometry. And every shape you see in nature has a fractional dimension, okay? So now what I'm going to do is I'm going to do something that's going to be a hard pill to swallow, but you can do because you can always do thought experiments, right? Imagine now I had this chip where I had this set of blocks. But now what I'm going to do is I'm going to take the boundary of the US and I'm going to superimpose this on this. And wherever block crosses the boundary, I'm going to say that terminal is going to come out. Okay. I mean, I can always do this. There's nothing stopping me from doing it, right? So if I superimpose the US on the boundary of the US in this chip, and I say wherever it crosses a box, I'm going to say that terminal is going to come out to the very edge of the chip. Then I've created a situation where the number of terminals is going to depend fractionally on the number of blocks within this chip, within this area, correct? And you can show that now I've created a situation where the number of terminals and number of blocks are related by something other than 0, 0.5, and 1. Okay. So if it exists in this case, any possible number can exist. Okay, this is a typical existence proof. It's not a proof, it's showing it can exist. In this case, it would be T and B are related by 0.769. But you can show that any random connection, any random architecture will have this relationship between T and B that has some power law dependence of some number between 0 and 1. Okay. That's like the conclusion of this whole thing. So, okay. So, and that is called as Renz's rule. Okay. So now, now that we understand a little bit about what Renz's rule is, now I'll talk about your point, right? It's called system partitioning. So when you have a very complex interconnected chip, right? So imagine this is like a bunch of logical blocks. So there's a guy, there's a team in every kind of company called the EDA team. Mm-hmm. And what the EDA team does is when they look at the design of the chip, they decide which portion of this is the entire design, okay? This is the entire system. So what the EDA team does is they decide which part of the system is going into which chip, okay? So they can put a bunch of boundaries here. So say that this part of the system is going into chip 1, this part is going to chip 2, this is chip 1, this is chip 3. And what they do is they use a very complex optimization algorithm where they minimize the number of chips, but also at the same time, they choose the chip in such a way that the number of terminals coming out is also less, okay? So it's a very complex optimization problem. You need to decide how many chips to have, where to place the chip boundary, how many terminals come out of the chip. You cannot also place chips very far away because communication becomes a problem. So you have to consider a whole bunch of different variables, and then they have a very complex cost function that they then optimize. Right? That's how that's how every chip design is done.
When you say chip, you mean like a single chip package?
It's a chip. When I say chip, it's a die. Yeah,
One
which is going to be packaged. Yeah,
Okay, so it's just one.
yeah, correct. It's just one die. Yeah,
All the logic blocks on the die.
yes, correct. Yeah. So this is clear, right? So ultimately, designing an entire system is all about deciding so this is the full system, this means it's memory, compute, whatever other stuff you have, everything together. If I could put this kind of a graph showing how everything is connected, then ultimately the problem comes down to deciding which portion is going to which chip and deciding the boundaries of the chip so that I minimize the number of terminals coming out of each chip, right? Because I want to minimize the connections. Okay.
This what IC engineers do?
This is what EDA team does. So it's basically, yeah, I would say VLSI, right? So a lot of this comes in something called VLSI design automation. A lot of this is done also by software. Like, most designers just use EDA tools to do this. Yeah.
Could you reiterate why it is beneficial to have less terminals on the boundary?
Oh, that will be explained next slide.
Next
Yeah,
slide.
I'll show you why. Yeah. Okay. Now here's something I found very interesting, right? Is if you look at a single logic block within a chip, a digital chip, right? And compare it with a single logic block in your brain, for example. So what's a logic block in your brain? It's a neuron, right? Yeah. If you compare the neuron, the way neurons are laid out to the way logic blocks are laid down, each individual neuron is not very complicated. In fact, it can be replicated digitally as well. But what cannot be replicated is the number of terminals, okay? So in a chip, you're looking at probably 1,000 terminals coming out of a modern chip. But if you can somehow put a boundary around a portion of your brain and see how many neurons are connecting out, it could be hundreds of trillions, okay? That's what makes the fundamental difference between why the brain is so efficient versus these kind of digital systems, okay? Like the power of the brain comes from the number of connections between the neurons, not really the neurons themselves, okay? That connections cannot be replicated by using these kind of artificial methods, right? Yeah, but you can still do it, but you just build very large systems. Yeah.
Have they always done it with squares? Have they not tried it with like hexagon?
No, this is a representation. Yeah. So this is just saying there's some logical block here. It's some complex circuit, right? And it's just a connection. Yeah. But now I'll explain your point, right? Why you want to minimize the terminals. Okay. So imagine now you were in 1960s, right? This was your chip. It has 16 blocks here, 16 blocks there, and this is your PCB. Okay. So you have these are the terminals, these are terminals on the PCB, and so on. And then life was very easy because you can just use the PCB to connect the two chips, right? So I connect this over here, this over here, this over here, go through the package and PCB, and then connect to this chip, right? But here's the problem. From 1960s all the way to today, because of Moore's law, every 2 years the number of transistors is double. So the number of transistor chips, the number of logic blocks within this area went from 16 all the way to probably 1 million. And so now what's the issue is, though that has scaled, and because of Rend's rule, as these blocks are going, the number of terminals is also going to increase. This has not actually scaled because this does not follow Moore's law, right? Because Moore's law only holds when you do lithography, when you do semiconductor processing. There's no concept of Moore's law when you do packages, right? All these are mechanically made. It's like, I showed you the drilling process and all that, right? So this is not scaling as fast as this. So now what's going to happen is as I go up in technology, you're going to reach this situation where now I have everything scaled down because of Moore's law. I have an enormous number of connections now, but now I have a package that has very minimal connections, right? So now how I'm going to connect the two chips together. But it's still done. How is it done today?
You shot the entire perimeter.
No. If you short, you lose those data. Every time you short means so if you have n signals coming out, if you short them means you converted them to one signal, right? You're losing all that information. You still want n signals out. Yeah.
Were you asking?
Yeah, I'm asking a question. How is it done?
Isn't it Sarah does,
Yeah, SerDes.
30s?
Yeah. So simple way how you can do this, if you don't have enough connections here, but you have a whole bunch of terminals here, what you can do is you can pair 4 of them together into one, right? And that's done with something called as a SerDes, serializer, deserializer. Okay. So what you do is so imagine you had 4 terminals coming in or 5. What you do is you put it through essentially a multiplexer is just a switch, and the switch just keeps moving up and down, so it keeps scanning up. So imagine you're getting you're getting one signals here, then you're taking these signals and this is moving 4 times faster, and then you're just converting these parallel signals into serial signals, right? And then you're sending out. Okay, but the problem with this is if say over here I'm getting 1,000 bits in 1 second, I'm getting 1,000 here, 1,000 here, 1,000 here, 1,000 here. If I want to maintain the same data rate, what should be the data rate over here? It has to be 5,000, right? Because over here I had 4 separate channels, 1,000 each, with a total of 5,000 bits per second. But now I have just one channel that has to carry the same data rate, means this channel is now going to operate at 5,000 bits per second, right? So originally I had each parallel channel operating at a low frequency. Now I have one channel that's operating at 5 times the frequency, right? So what is the issue with that? That's one issue, but remember I talked last class about what is the issue with doing high frequency?
Bit loss.
Yeah, bit error rates. Designing the line is very difficult because as the frequency gets higher and higher, as I mentioned before, right, every little thing in the line matters. So a single bend in the line itself can destroy the signal, right? And then you're going to have a lot of loss. So as the frequency goes up in going from one side to the other, your signal is going to start decaying in power a lot. So you have to boost the signal. So it consumes more power to amplify the signal and so on, right? And also the SerDes itself is pretty large, okay? So to design the SerDes, it's a very large circuit. And so if you look at a modern chip today, how much area on the chip do you think the SerDes occupies in terms of percentage? Yeah, it's like 30%. So 30% of chip area doesn't go to compute, 30% of chip area just goes to making the SerDes to communicate, right? And so you have a loss of chip area. It consumes 30% of the chip power. So it's consuming unnecessary area, power, and then also it basically makes the design itself more complicated. Yeah.
So, because there are 5 lines here into it's like a 5:1 marks. So, won't that like select bit need, there should be 3 select bits.
Yeah. And the select bits also have to change at a certain frequency, right? Because you have to select each one. I mean, the circuit is much more complicated than just the marks, but simply put, it's just a switch that switches from one line to the other. Very fast.
Is there like a set number in terms of how many terminals are connected, or does it change design to design?
No, design to design. It can be designed to anything. But the thing is, the more terminals input, the higher the frequency here, it becomes more difficult to design it. Yeah. And so here, this is a graph that shows, actually, there's an actual calculated graph that shows how silicon has scaled. You see how silicon scaling is almost on an exponential logarithmic scale. So initially, this is a relative scaling. So if say the original size is 10,000, it's scaled all the way to 1. So it's a factor of 10,000 scaling down of the dimension of the transistor. But if you look at packaging, it's remained almost the same dimension in the same time, right? So there's an inherent mismatch between the scaling of the chip and the scaling of the package, right? And therefore you need something called SerDes. So essentially now you connect these SerDes. Each SerDes now takes 4 lines together, converts it into 1 line, and now you can use the limited lines here, right? But the caveat is you have to serialize it, send the data much faster, and then deserialize it here, and then send it over here, right?
3 marks.
Yeah. Yes.
Might be a stupid question. Is it always 4 for a reason?
No. It can be anything.
Okay.
Yeah, it's just I don't want to draw like 25 or something.
This must be another stupid question. What is specifically preventing you from increasing the number of lines on the PCB package?
Oh, because you're limited by manufacturing.
Okay.
See, the thing is, you can't drill a hole smaller than the
Oh,
drill
yeah.
bit, right? But lithography, if you use lithography, you can do any size. You're limited only by light, right?
Right.
That's the limitation.
I got another stupid question. What is more limiting, the wire or the PV packaging at this rate? Like, what's the bottleneck on,
So when I say PCB or package, this includes everything. So I'm talking about the various levels of, this is just a representation again. So I'm representing this. I'm just trying to say that this is representing the fact that the package as well as the PCB have limited number of connection nodes, right? So so when I say this is, when I talk about this terminal, this is talking about M17 on the chip, right? Which is at 1 to 2 micron. You remember from my previous talk. So I'm going from M17, which is at 1 to 2, all the way to something here which is in hundreds of microns, right? So because the number of terminals here is so large, the only way to do that is to serialize it and then send it through the limited number of bits. So, this is how it's done today using SerDes. And the issue with SerDes is it's very complex to design. The thing is, this also has a limit. As the scaling continues and chips are getting more and more complicated and more packed together, right? You have more terminals, and and because the package is not scaling quickly enough, you're having a situation where the SerDes is operating at extremely high frequencies, and designing the SerDes becomes very difficult.
Is there like a certain bit rate that's just is all worth it, or is that?
No. It's just you have to do. So SerDes is an extremely complicated subject, okay? Because there's something called equalization, and like it's extremely complicated. It's a whole bunch of mixed signal electronics design. But there are ways to overcome it. But you have to kind of you have to add more error correction codes. Okay, so the bits are going to have more errors at high frequency, but you add more error correction codes to those bit streams to correct those errors. But adding more bits increases the frequency, and it just gets more complicated.
And these SerDes are like built onto the chip. They're not like physical interconnects.
No, it's an actual digital circuit. It's a digital and analog. It's a mixed signal circuit that's built on the chip. Yeah. So if you look at a typical chip layout, right? You'll have like, if you look at an Intel, any chip, it's like it'll have compute, it'll have some memory here and so on, and it'll have something called I/O blocks, input/output blocks. Those I/O blocks are all SerDes.
Right.
Right.
Which you can, in that sense, you can technically scale the size of SerDes because it's related to lithography in terms of like how small you can get those.
Oh no, SerDes doesn't scale like that. That's the problem.
Oh.
Because that's a good point actually. SerDes does scale, but yeah, SerDes does scale, but the problem is it still occupies a huge portion of the area of the chip. Yeah.
Please talk about fan in, fan out. So if now you said that was M17, if that was M17, then after that would be the fan out, right?
No. Fan in and fan out is happening here. This is not fan in. This is, you just have so many terminals that you cannot even fan out. There's so many terminals. See, fan out means what, right? Fan out means, if I draw it as a representation, right? If I have 4 dots here, and then I have 4 small dots here, then I connect them like this. This is fan out, correct? But imagine I had 1,000,000 dots here, right? I cannot map it to 4 dots. So I have to take a whole bunch of dots, make them into 1 dot, then I can take it there, right? So that process of mapping large number of dots to a smaller number of dots, that's done by the SerDes. And then to take it to the pitch that you want, that is done by the package, right? We can do this in multiple levels, right? Yeah.
Now I'm having trouble understanding the device on the left versus the device on the right. So just say like the middle is like just like a motherboard, or is this?
So there's a representation for everything. So if I was to like draw this out here explicitly, right? So if you look at a typical flip chip package, for example, so there's a die, and then you have like this kind of bumps, and then there'll be a laminate, and then this goes on PCB, and then here on this side you'll have the same thing over here for another chip, right? So you have laminate, and then bombs. So this is chip 1 and this is chip 2, right? So the SerDes and all that is on the chip itself, right? So say inside the chip there's a logic block. It goes to the SerDes. The SerDes serializes it and then sends it to one of these 4 pins. And then from these pins, it fans out over here. Then it goes to the PCB, comes here, fans in, goes into the chip, then goes to the deserializer, which takes it from serial to now parallel, and then provides it to the logic block within this chip.
So the blocks are the last metal one, right? And then the red square is like C4 block.
Yeah, so Renz's rule applies to on the chip itself, how many terminals are coming out, right? And then to if the terminals are so large, then you serialize them. And then from that point onwards, you just take it to whatever links are on the package. Right? Renz's rule is I'm talking about within this chip area. Yeah. So adding on to this, right? Yeah. So because of all these issues, right? Because of the fact that say I was NVIDIA, right? And I was designing a GPU chip. Say this was the actual compute. So this was one of the compute processors, compute logic blocks, and this was supposed to be memory, right? What is the issue of having this kind of a situation, right? The issue is GPUs process graphics, so the calculations have to be done very, very fast. So if you do this kind of setup, what happens is every time the compute chip has to take data from the memory, it has to go through all this long links and all that, and it adds something called latency. So it adds more delays, right? So your chip won't operate that fast because it has to go through this long links to go and fetch the data from the memory, bring it all the way there, process it, then go all the way back and store it here, right? So what they do is rather than having this kind of situation, they take everything and put it on one single chip, okay? And that's why the NVIDIA GPUs are huge. Like if you look at a typical NVIDIA chip, it's almost like 100 millimeter by 100 millimeter. Yeah, it's like 800 square millimeters, right? That's pretty big for a single chip. And that's also why the GPUs are so expensive, because if you make the chips larger, per wafer, the number of chips that yield reduces, right? Because the cost per wafer hasn't changed, the cost per die or the cost per GPU is now higher. That's why the NVIDIA GPUs cost like 3,000, 4,000, right? It's because the chip itself is very large, right? So, so for example, here is a graph that shows you how the chip area has changed with the year of introduction. So for example, in 1995, a single chip had just 1 million transistors, and the chip area was 100 square millimeter. But fast forward today, you're looking at chips that are almost 820 square millimeters with 100 billion transistors, right? And the reason why the chips are becoming larger and larger is because the package hasn't scaled. So you don't want to do off-chip communication because it's going to be more complicated and time-consuming and energy-hungry. So you want to put as much functionality within the chip itself. And so if you remember Renz's rule, if you put more and more functionality within the chip and you make the chip almost self-consistent, then you can reduce the number of terminals coming out, right? So that's the approach today. So in most cases, this is the approach that's taken. You just connect them with the package with the SerDes. But in cases where you care a lot about the communication latency between blocks, you put everything on one chip because of the enormous sacrifice you have to do to go off chip. But the caveat of doing this is that when you make these chips this large, because per wafer, because the cost of the wafer hasn't changed, the number of dies coming out of the wafer has reduced, the cost per die is now gone up significantly, right? So if there was a way that you can overcome this and make this dense, almost matching the number of terminals coming out here, then you don't have to go to large chips. You can use a whole bunch of small chips, connect them together at high density, and you can reduce the cost of the system. You can avoid the use of SerDes, you can improve the power, you can improve the energy, and that is where this industry is slowly moving towards, right? That is why you see so much interest in advanced packaging today, because Moore's law, which is scaling this down, is no longer going to go because transistors are almost approaching the size of few atoms, right? And you can't make it smaller than an atom, right? So this is stalling. So how do you improve system performance? How do you get the boost from system performance, cost, energy, and power? You start scaling this package down. so that now you can have everything compact and you can now connect them without the use of SerDes and all that, right? And that is, I think that is the best way to understand what advanced packaging is actually. So now I'm calling this advanced package, and throughout the rest of the course, you see how you make this. Now we have an advanced package, which is not a PCB, it's a different kind of substrate. Usually, for example, silicon is an example. And so now you have the same kind of densely packed chips, but now you have a dense number of interconnections. So you no longer need SerDes. You can just map one terminal onto the next, right? So now you have enough connections here that you can just connect these directly without the use of SerDes, right? And so now you can use small chips, but you can also connect them as if they were on one single chip, right? So future is going from this to going to something like that. And this is actually not science fiction, it actually exists. So this is actually from my former group in UCLA. So in UCLA chips, what we did is we took a system that's an entire rack, server rack, and put it on almost one single wave. Okay. So imagine now you're going from back then, right? If you look at the computers in 1960, they occupy a whole room, right? And now everything is on this desktop and it's way more powerful, right? Now imagine the future where a whole server rack or a server is now on your desktop, right? Because of how fast AI is advancing, eventually this is the place where we have to go, right? And that's the only way that we can, also you have to consider for modern AI the power costs, right? If you can save that 30% power, that's an enormous power saving overall, right? So this is eventually the kind of place where we want to go using advanced packaging. So any questions so far? Yeah.
So that would be the remove. Like we said, that 30% area reduction,
Area power.
is that, you don't have the SerDes anymore? Or?
Yes, it's mainly because of SerDes. Yeah. Because SerDes has to communicate, SerDes has to communicate over long distances, right? So it has to boost the signal. One, because the length is long, two, because the frequency is higher, right? So because the length is long, frequency is higher, the signal is going to get weaker and weaker as it travels, right? So if you don't boost the signal, then by the time it reaches the other chip, the signal is gone, or it gets merged with the noise around the whatever. You guys have heard of signal to noise ratio, right? So if you want to get a good signal strength at the receiver end, you need to boost the signal with a higher power so that it goes all the way to the other chip, right? So there's a cost of power associated with that. So yeah. Yeah, that's why that's the area cost. So SerDes has an area cost, which is 30%, because 30% of the transistors on the chip are now used to make the SerDes, right? Which is completely unnecessary, actually.
How we can become these advanced packaging, when we stack up the chip, do we also get rid of the layer of silicon?
Yeah, you will remove the multiple. So in this case, I don't know what happened. Did it switch off?
So you're sharing something.
No. I was not sharing today. I was recording it. That's weird.
That's like, you know, wait for the other.
How does the heat transfer